Okay, in this second video of chapter 5, I'm going to show you some basic concepts about graphs and graph theory. Graphs are the mathematical objects used to represent networks, and graph theory is the branch of mathematics that deals with the study of graphs. Introduced in 1763 by Euler to set a famous unsolved problem of his time, the so-called Königsberg Bridge problem. So I'd like to invite you to watch the video 3. You can get the link from the PDF slides. So it's just to show some more details about Königsberg Bridge problem. Subsequent work in graph theory by Kirchhoff and Cayley had its root in the physical world. Kirchhoff's investigation into electrical circuits led to his development of a set of basic concepts and theorems concerning trees in graphs. Framework for the exact mathematical treatment of complex network is a branch of discrete mathematics known as a graph theory. So, example 1, 7 people have been invited to a party. The names are Adam, Beth, Cindy, David, Elizabeth, Fred, and George. Before meeting at the party, Adam knew Betty, David and Fred, Cindy knew Beth, David, Elizabeth, and George, David knew Betty, and of course Adam and Cindy, Fred knew Betty, and of course Adam. With this example, you can make this figure 11. So you can just make adds between the nodes to connect. So in this graph, if you can use in this scheme A, or you can represent the letter B here. So this is a friends at a party. In the example 2, the map in the figure shows 23 of Europe's approximately 50 countries. Each country shown with a different shade of gray, so that from image you can easily distinguish the borders between any two nations. So in this here you can see, for example, that Portugal has just borders with Spain. So in this graph you can see here, it's easily to see that in this point you are going to see just here, it's easy to see that you are going to see that in this area of the graph, the connection between Portugal is only with Spain, and Spain is only with France. On the other hand, France has many here connections, but probably one who has the most connections is German, here letter D. Right. So definition 1, an undirected graph, a graph, more specifically an indirect graph G of N and L, consists of two sets, N different from 0, and L, the elements of N, N1, N2, and 2N, are distinct and are called the nodes, or vertices, or points, of the graph G. The elements of L, L1, L2, to Lk are distinct unordered pairs of distinct elements of N, and are called links, or edges, or lines. The number of vets N, or Ng, or just N, where the symbols dot here denotes the cardinality of a set, is usually referred as the order of G, while the number of edges K of G, or just L, is the size of G. In an undirected graph, each of the links is defined by a pair of nodes, I and J, and it is denoted as A and J, or Ji. Two nodes joined by a link are referred to as an adjacent or neighboring. So here you can see 4 examples of networks. In the example 1, G1, you have 5 nodes, and the node 1 is connected to 3, 3 is connected to 1, 2, and 4 is connected to 5, right? So some examples of indirect graph, namely tree in the net G1. 2 graphs contain cycles, G2 and G3, and indirect multigraph, because in this sequence here, the number 1 is connected to itself. Graph G1 is made of n5 nodes and k4 edges. Any pair of nodes of this graph can be connected in only one way, so it's a tree. Graph G2 has n equals to 4. By starting from one node, say node 1, one can go to all the other nodes 2, 3, and 4 and back again to 1. So G2 contains a cycle. Graph G2 has n as well 4 and k3. So there is 1, 2, and 3 edges. Graph G3 contains an isolated node and 3 nodes connected by 3 links. G3 is not connected. Graph G4 has loops and multiple edges, so G4 is a multigraph. Node 1 is connected to itself by loop, and it's connected to node 3 by 2 links. For a graph G of order n, the number of edges k is at least 0, in which case the graph is formed by n isolated nodes, and at most n times n minus 1 by 2, when all the nodes are pairwise adjacent. The ratio between the actual numbers of edges k and its maximum possible number is known as density of G. An empty graph, of course, the density equals 0. A complete graph denotes as Kn, its density is 1. So this is a complete graph of 3, 4, and 5. So all the nodes has all the possible connections. Box 1. It's quite important to have useful tools to make some graph drawing. A good drawing should highlight parts of a graph. Example, circular layout, this here, and a spring-based layout, this one here, based on the command away algorithm. Soft packages, so there are many soft packages here. One that I like, it's quite easy to use, is this Pajek, P-A-J-E-K. So from the PDF slide, you have access from all these sites, right? So it's quite useful to take a look of them and to try to choose one for you to take a look. Comparison of graphs. How to compare graphs with the same order and size. Two graphs G1, G2 are the same graph if just N1 is equals to N2 and L1 is equals to L2. In this case, G1 is equals to G2. So here you have 3 graphs. Let's see what happened here. Graphs A and B are the same graph, since the edges are the same. Graphs B and C are isomorphic, since there is a adjection between the nodes that preserves the edge set. Definition 2. Isomorphism. Two graphs G1 and G2 of the same order and size are said to be isomorphic if there exists a bijection phi that transforms N1 to N2, such that U and V belongs to LF only if phi of U and phi of V belongs to L2. The bijection phi is called isomorphism. The adjacency is preserved. In this case, we write G1 is equivalent to G2. Two labeled graphs, namely the cycle C4 and the star graphs S4, and one possible labeling of such two graphs. It's difficult to check whether two unlabeled graphs are isomorphic, because there are n factorial possible ways to label the n nodes of a graph. This is known as the isomorphism problem. There is no algorithm to check if two generic graphs are isomorphic in a polynomial time. Definition 3. Automorphism. Given a graph G, An automorphism of G is a permutation phi from n to n of the vertices of G, so that if uv belongs to L, then the function phi of u and the function phi of v belongs to L as well. The number of different automorphisms of G is denoted as A of G. So here you can see 4 nodes and 4 edges. In this case, 2 is connected to 1 and 3. And here is the same, 2 is connected to 1 and 3. But in this case, as you can see here, this is just a shift of the labels, and all the connections are preserved. So all possible automorphisms of graph with C4. A subgraph of G is a graph G-line that n-line and L-line such that n-line is contained in n-line. So L-line is contained in L as well. So here is just a small mistake. Consider this part here, right? Here is not n-line, and here is not L-line. In fact, it's just L, okay? And if G-line contains all links of G, the joint 2 nodes in n-line, then G-line is said to be a subgraph induced and generated by n-line, and is denoted G of G n-line. So, for example, a subgraph here, a graph G with 6 nodes and 3 subgraphs of G. So, for example, if I take out these dotted lines, so you can put another subgraph, and you can produce from graph A 3 other subgraphs. So here, this is the way that I'd like to finish this second video. So just to give some more basic concepts of complex networks. I thank you so much for the attention of this video, and I hope that you can see the next video as well.